Did he say, so you'll have to always tell me what they say. So he said they're almost ready, but then it sounds like the other fellow said no.
I don't know. I think they'll do I thought they were gonna do the countdown.
Ready in 5, 4, 3, 2, 1.
Welcome, my name is Heather and you are here with Circle Passages and we're talking about the circle of the earth. And I'm here with my good friend Pat. Pat and I met at the Children's Museum where she was Dr. Science and I was the muralist. And we're going to tell you the story of the atmosphere. And what we'd like to tell you is what it is, how it's changed, and also we want to come up with why it's important. Not only the what, the where it came from, how it's changed, but why. Why do we want to know about the atmosphere? And so this is our great quote for that. And it's from Jim Henson, not from the Muppets, but from NASA, and it's our future depends on an understanding of our air. And so air is our topic, and I'm going to be the graphic illustrator. My job is to make the invisible visible through my illustrations, and I will be drawing here. Pat is going to be narrating, and she's going to be telling a story, something she is uniquely gifted at because she's been blessed by 40 years of storytelling and answering questions as Dr. Science at the Children's Museum. So with that, Pat, welcome.
Thank you, Heather. So we're going to begin. Welcome to Atmosphere 101. So we're, as Heather said, educators at a children's museum, so we're not going to assume any prior knowledge of atmospheric sciences. So we'll begin by basically defining just what an atmosphere is for you. So Heather's going to start. She's going to start by drawing the planet Earth. And so here comes planet Earth and its atmosphere. And an atmosphere is actually a layer of gases held to our planet by gravity. So recently, Jeff Bezos shot himself through our atmosphere. So I'm just going to wait till we get the planet on there a little bit, and then we're going to shoot Jeff Bezos out into space. Here he goes. There he goes. Okay. And on returning, he said, the atmosphere is so gigantic, but when you get up above it, what you see is it's actually incredibly thin. It's this tiny, little, fragile thing. Now we're going to post a photograph here, and it shows you two Earths. The one on the left is how we imagine the atmosphere. So when I think about the atmosphere, I'm going to switch it. That was actually upside down. The one on the right, I'm sorry, that's
Sorry.
okay, no problem. The one on the right shows what we think the atmosphere looks like. The one on the left that has this very, very thin line, that's a more accurate depiction of the real tiny and fragile thing. So all life lives in the lowest level of the atmosphere, the troposphere, which is only 5 to 10 miles deep. Which I looked it up the other day, and that's how far it is to my local food co-op. So we're not talking, our atmosphere is not a huge thing. Our atmosphere itself and everything on Earth is made by combining 113 small ingredients. And so we're going to be posting these ingredients. It's the periodic table, is a list of those ingredients. And one of them is carbon. And it's very important in putting together living things. And that's why it's referred to as the duct tape of life. So Heather's putting in the little carbon atom there. So you're going to be hearing a lot about carbon because it plays an important role in our atmosphere. Every part of your body and every living thing is made up of chains containing carbon atoms. So, yeah, so now we're going to go for, so here we're going to get to see. So this is an example of a molecule, and it's a hemoglobin from your blood. We wanted to put a few science-looking things up here. So that's basically a carbon chain. And everything alive is made out of these chains of carbon. That's why when aliens in movies come down to Earth, they refer to us as carbon-based life forms. So like duct tape, carbons hold atoms together very tightly. A carbon uses a lot of energy to make these bonds that are in these molecules. When you break them, the energy gets released. So when you burn wood, the light, the heat, the sound, they're all the result of energy being released from breaking bonds. And remember, we have the duct tape here to remind you that these are very, very tight bonds. So carbon is very strong. That's our carbon atom.
Oh.
So that's my idea what a carbon molecule looks like. So the bonds are so strong that even when any of these living things, a plant or an animal, dies and gets buried in the ground, even for a long time, the carbon atoms still stay locked together. That's why there's still energy in dead and buried plants and animals that we extract from the ground. And we call these buried plants and animals coal and oil. Okay? So carbon atoms are also really important to our atmosphere. An atom of carbon loves to combine with 2 atoms of oxygen, and that makes carbon dioxide. So we have another little figure here, and that is our carbon dioxide. So there's the carbon in the middle, and the oxygens, there kind of looks like his ears. So when the carbon dioxide is up in our atmosphere, it captures heat from the sun and helps warm our planet. Without the greenhouse gases like carbon dioxide, our planet would freeze. So, carbon atoms. They're important for 3 reasons. Number 1, they build all living things. Number 2, they store the energy of the carbon bonds. So in those tight bonds, they store energy. And 3, as carbon dioxide, they help warm our planet. There we go. So, chapter 2. What plants do? It's kind of like a poem.
Oh, okay, let's go leave that.
So at this point, you may be asking yourself, I thought this was about the atmosphere, so what have plants got to do with it? So we're getting ready for Heather to get the next board. So it turns out plants have a lot to do with it. And so we're going to begin with a really big plant, the tree. And Heather and I spent a lot of time out talking to people about carbon cycles and the atmosphere, and we discovered that the tree was the best vehicle that we had for explaining these things to people. So we always begin with a tree. Now, all life, all plants, all animals require energy. On Earth, the source of our energy is a continual nuclear explosion 93 miles away. And we call that the sun. So here comes our sun. Plants plug us into the energy of the sun. How do they do it? They do it through a process called photosynthesis. So here we are with our scientific formula here. Photosynthesis. Now, you probably studied photosynthesis when you were in science class, but that might have been a while ago. So this is the way we like to explain it. And we begin with a question. A small seed grows into a massive tree. Where does all the material mass of that tree come from? So we're going to ask you, what do you think? So most people guess that the mass of the tree comes from the soil. And that's actually what we thought too, wasn't it? Mm-hmm. But it turns out that 93% of the chemicals, and those chemicals are mostly carbon, that make up the dry weight of a tree come from the air. They come from our atmosphere. Yep, plants, trees are all built out of the atmosphere. And here's how it works. So we're going to put a leaf on our tree there, right there under the sun. And on the bottom of that leaf, there are tiny holes. And those holes are the way in which the plant breathes in the atmosphere. So they basically are sucking in the carbon dioxide from the air through those holes. And here's what happens. So we're going to get a close-up here of photosynthesis. We're going to put the, yeah, there we go. Yeah, there we go. And they take in carbon dioxide and they give off oxygen. And here's what they do. So Heather's going to point to this formula as I go. Yeah. Yeah, that's okay. She's getting it on there. And we were going to just use like one of these things so you can.
Oh, yeah.
There you go.
Should I underline it?
No.
No.
Yeah,
Okay.
we'll just point.
Yeah.
Yeah. So even with the cap on, you could, yeah, with those, that'd be perfect. Yeah, great. Okay, so taking the energy of the sun and taking the water that comes up through the ground, okay? They mix that with the carbon dioxide that comes out of the air. And when they combine that, so water and carbon dioxide, using the energy of the sun, they turn it into sugar and oxygen. Now the sugar, and you may have tried maple syrup, that would be an example of it, are the things that the plant uses to build the plant. So that's what the plant is constructed from. And then a lot of the sugars are also put down, and they go down into the fungi and the mushrooms and into the ground to be used underground. So light of the sun, the energy from that combines the water and carbon dioxide, and the tree makes sugar, and it gives off oxygen. This chemical process leaves the waste product oxygen, which the leaf releases back into the air. And so the plant basically performs an atomic miracle. They use sunlight to create the food we eat and the oxygen we breathe. So we as animals are not able to do that. Only the plant can plug us into the energy of the sun. We have to either eat a plant or something that ate a plant. Okay, number 3, life creates air.
Oh, okay.
So while Heather's switching over to the next one here, I'm just going to go on top. Perfect. We've talked about what plants do, and now we're going to add to that what animals do. And we'll see what we get. So I'll help out with the postings here.
Okay.
Can we go
thank
this
you.
way?
Yeah.
I think so.
There, gorgeous.
There we go. And that's one you post.
Perfect.
Perfect. So Heather's going to post that formula there for us. So chapter 3 is called Life Creates Air. So here we go. Animals breathe in that oxygen that the plants have made, and that begins the formula for respiration. Respiration, so if plants do, and actually plants do respiration at night, but they do twice as much photosynthesis, so that's how we get the effect in the atmosphere. So respiration, that's what people do. So we breathe in the oxygen, and we eat sugar by eating a plant or something that ate the plant that created the sugar. And then what happens is that we then breathe out carbon dioxide, and then we also expel water, and we use the energy, and that's respiration. So the interesting thing about this is that you don't have to remember these formulas. The important thing to notice is that our breathing is the exact opposite of a plant's breathing. So if you read this formula backwards, you get the formula for photosynthesis. And here, it just occurred to me, I can do this part. So look at, if you do it backwards, you start with, the plant started with the energy of the sun. It took water from the ground, combined carbon dioxide from the air, and it gave off sugar that it created and used to build the tree, and oxygen that it released into the air. So respiration this way and photosynthesis that way. And round it goes. Plants produce the oxygen we need, and we produce the carbon dioxide they need. It's called the carbon cycle. Here we go. There's our plant. Go. Perfect. Okay, so now we're going to add to the Roman philosopher Plotinus on a little pillar here. So the Roman philosopher Plotinus said, "The whole world breathes together." I thought it was a beautiful quote. Well, these two amazing and invisible processes, plant photosynthesis and animal respiration, work together to create the contents of our atmosphere. And the movement of the molecules through the carbon cycle helps to keep the levels of carbon dioxide and oxygen in balance. Plants and animals create our atmosphere. Our atmosphere was made for us because it was made by us. And that's why we have the perfect atmosphere for us. Chapter 4, the flow of parts.
We're going to go shiny side out.
I think that helps if I do that, huh?
Yeah. Okay.
So in watching the processes of photosynthesis and respiration, we now know that molecules continuously flow between all living things. What does this physically mean to you? So if you take a breath, so breathe in right now, everyone. Take a deep breath in. Heather gets to breathe in too. You've just inhaled approximately 12.5 sextillion molecules. Okay, you can exhale them now. That sextillion is a lot. It is 1 followed by 21 zeros. Molecules are extremely small, and small things are present in our atmosphere in unimaginably large numbers, and that means an incredible thing happens. Every time you take a breath, you breathe in molecules that have also been in the breath of a humpback whale out in the ocean, or the weeds in your garden, because we know that plants breathe too. These molecules are the same molecules that have been moving through the atmosphere since the formation of the Earth. So they've already flowed through everything that has been alive in the past. They were in the breaths of Abraham Lincoln, a T-Rex, or an ancient ginkgo tree.
It's a clover.
That's close. Ginkgos actually look pretty much like that. And now they're inside you. And if that's not enough, these same particles will flow between everything to come. Plants and animals in the future will inhale molecules that have passed through your body. The extremely large number of these molecules guarantees it. We are constantly exchanging invisible molecular parts, but because we interact with the world through sight and hearing, we're not aware of it. We think of ourselves as separate. Einstein called this the optical illusion of separateness. Turns out the sharing of parts is a very old idea. Lucretius, and we were talking about them, this is a fellow who lived 99 years before Christ, so about 100 years BC, he said, "We are a bit of everything, and then we go on to become something else." So there's Lucretius. Read a whole book on Lucretius, amazing guy. Do you remember when we read
Swerve,
that one?
yeah.
Swerve. Swerve is a wonderful book. Turns out the sharing of parts is an old idea, but it's an idea that's come down through poetry and to our whole world. Walt Whitman wrote, "I celebrate myself for every atom belonging to me as good belongs to you." I saw a bumper sticker in the parking lot the other day that said, "What would Walt Whitman say about this?" And so this is why we added this one. This is what Walt Whitman says about all of this. "I celebrate myself for every atom belonging to me as good belongs to you." So I looked for a word that would describe this, and I came up with commingled, which turns out to be a term used in recycling, which is perfect because nature ultimately recycles everything with everything else. This one was just such an amazing thing to learn about. And if you want to see how these numbers work, I spent a lot of time trying to figure out how this all worked. Sam Keen has written a book about all of this, and it's called Caesar's Last Breath. So it's a fun book to read.
Are we on to the next one?
We're on to the next
Ta-da! These are not very colored in.
one. That's okay. We'll just keep going.
Okay. Okay.
Should I go slower?
No, you're perfect. Yeah.
So this is number 5, and we're going to give Heather a moment here. And 5, we're going to talk about, so carbon is very important. It builds everything, all living things, important to the atmosphere. It helps heat our atmosphere, keeps our planet from freezing. We are floating around in an immensely cold, empty, vast space. So we're going to ask the question, where does carbon come from? So we've been looking at the extremely small, and now we're going to step back and take a more majestic viewpoint by going for a quick, big history of where carbon and then where we came from. So I find it helpful at times when I'm struggling in the day-to-day news to relocate myself on a larger map like this. So sometimes I like to just think about the big picture. We're going to begin 14 billion years ago with the Big Bang. And the Big Bang created space, matter, energy, and time. And these came together to form our universe. In Latin, the word universe means combined into one. In fact, for 400,000 years, the universe was just one hot, undifferentiated ooze until it cooled enough to form the first simple atoms. So there's our undifferentiated ooze there. That came out very nice. I like that a lot. We had fun trying to figure out how we would illustrate all these things. So then comes our first atoms. So they were hydrogen and helium, very, very simple atoms. When they first appeared, the universe went from cloudy to clear, and for the first time, light streamed across space. So you have this basic ooze, and all of a sudden you find these particles collapsing down and forming the atoms. And light streams across space. That was one of my favorite things I read in the entire time of researching this. These new atoms came together and formed the first stars, which were hot enough for nuclear fusion. In the furnace of these first stars, bigger and more complex atoms were created. One of them was carbon. These first stars burned for a couple million years, and then, when the hydrogen was used up, they exploded, launching these new atoms in the form of gas and dust throughout the universe. So that's basically what a supernova is. And so if you've been reading this week about the new satellites pictures where they think they've actually taken a photo of a supernova, that is these original stars where first carbon was formed that shot across the universe. So they came to the spot where our solar system is now, and our solar system was formed from a cloud of gas and dust, just like this, that was nudged by something like a passing star, and it collapsed to form our sun, the earth, and eventually us. So as Carl Sagan says, the cosmos is within us. We are made of stardust. And he really means dust. We are all made from the dust of a star that blew up 8 billion years ago.
I was tempted to write R instead of R.
Yes.
It would be texting.
That's right. We are stardust. And we really felt like we had to include Carl Sagan
Ode
in
to
this.
Carl
It's
Sagan.
so an inspiration for everyone. And now we go to number 6, atmospheres change.
Okay. This is where things heat up.
Yeah. So our planet has actually had, I mean, people count it different ways, but basically three different atmospheres. So we have 3 ones. So when the Earth formed, its atmosphere was probably made from hydrogen and helium. You'll remember those were just the stuff that was out floating in space. And that was what was in space around the Earth when it formed. Both gases eventually escaped the Earth's gravity and drifted off. So that's goodbye atmosphere number 1.
Very hot.
Yes, it was very hot. Mm-hmm.
Okay. I'm going to use this for lava next, so we're going to do very hot.
Well, and I think it's important because you can go now find planets that this is their stage. And that's exactly what they look like. Yeah, exactly. So, Earth's second atmosphere came from inside the planet. And it came from inside the Earth. So volcanoes formed, and water and carbon dioxide and ammonia were released. And that formed our second atmosphere. And it would have stayed that way, except bacteria, an ancient form of bacteria, appeared in the oceans and began combining the carbon dioxide with sunlight and the water, and it started releasing oxygen. So recognize photosynthesis. This is the beginning. Photosynthesis is the beginning of the changing. And gradually oxygen began to build up in the atmosphere, and that led to our third atmosphere, the one we know and love, where plants create oxygen. But now in the current version, we add animals that take in the oxygen and release CO2, creating a balance between the 2 gases.
This is a rabbit.
He's cute. I like him. He looks like he's overseeing the. I like that one. Okay, Earth's atmosphere has changed dramatically in the past. Our first atmosphere came from outer space. Our second atmosphere came from inside the Earth. And now life creates and maintains our current atmosphere. So it's the rabbit in the tree. Perfect.
I'm going to finish these more and people can see them with greater detail.
And I think we're doing so well time-wise we can go slower. Yeah,
Oh, okay.
yeah, perfect.
Oops.
So our next question is going to be chapter 7 of our story. Where is carbon? Now, it's an extremely important question for our current atmosphere. Heather, we worked a lot on explaining to people what was actually happening in the changing of our atmosphere right now. And basically we came down to this 4-square grid. And for me, it's when I think of anything having to do with this, this is the way I organize my thoughts about it. So we're going to ask the question, where is carbon? And it's a bit of a trick question because carbon is always moving. Sometimes it's moving fast, and sometimes it's moving very slowly, but it's always moving, cycling around. Okay. So these 4 squares that Heather's just drawn are the main places that carbon can be on Earth. So the first one is biomass on land. Half of the dry weight of most living organisms, plants and animals on land, is carbon. So you're always hearing about how the forests store carbon, and we think of the forest trees.
These are supposed to be trees.
It's a nice big tree. Oh, that's lovely.
And these are more rabbits,
Yep,
in
these are
case
rabbits.
anybody wonders.
There you go. They look rabbity. So number 2 is underground. So there's a lot of carbon in forest trees, and that's what we normally think about. But surprisingly, most of the carbon in the forest is in the soil. And you remember that picture back when we showed how the carbon was made by the tree and was used to form the tree? Up to 70% of their carbon can also be stored. The tree sends it down through their roots into the ground, into the mycorrhizomes underneath the ground. So a huge amount of the carbon is stored there in the bottom. And carbon is also found underground in buried plants and animals that decompose to become fossil fuels. When a carbon molecule is stored in one location for a period of time, scientists call it sequestration. We didn't get into a lot of vocabulary words, but this is one that you really need to know.
And trees are called sequestration experts.
Oh, that's true. Yeah.
Yes.
Yeah,
This is
yes.
a Dr. Tree.
Yes. Because they do it so well. And a place where it's stored is called a carbon sink. So we could also call a tree a carbon sink. So buried carbon is a very important carbon sink. Carbon may be sequestered 100 years in the tree itself, but carbon sequestered in the soil can remain out of the atmosphere for 100 to 200 million years. And we'll come to talk about why this is our goal, is to move the carbon out of the soil. Out of the atmosphere. So 3 is the air. In the atmosphere, the carbon takes the form of a gas, CO2. And when we talk about that gas or measure that gas, it's invisible, we can't see it in the air. We talk about the amount of CO2 in parts per million. So as we refer to the amount of carbon in the air, we'll start to talk about parts per million. Our 4th place and last place that the carbon can be stored is the ocean. And oceans store huge amounts of carbon in its biomass as dissolved gas and as sediment that falls to the ocean floor. So it gets absorbed and becomes part of the plants in the ocean. It falls to the floor of the ocean and gets buried. And it also resides as a form of gas within the ocean. Humans aren't creating new carbon. We are changing where the carbon is. We are pumping the oil and removing coal from underground, and when we burn it, it releases CO2 into the air. So now we're going to do an oil derrick here. So those are buried plants and animals, and we're now bringing it up and releasing it as we burn it into the air. We're also cutting down and burning forests. And carbon is moving from being stored underground and in biomass on the land. So it's moving from underground and in the ocean into the atmosphere. And from the air, it then moves into the ocean. The content of our atmosphere and oceans are changing. 162 million tons of invisible human-caused global warming pollution goes into our atmosphere every day. That's 162 million tons every day. Between 1/3 to 1/2 of human-made carbon dioxide is being absorbed by the ocean. Because of this additional CO2, the oceans are becoming more acidic, making it hard for marine life to form shells and skeletons. 1/2 of our oxygen comes from the ocean. When asked why care about the state of the oceans, deep sea explorer and biologist Sylvia Earle replies with the question, "Do you like to breathe?" So we have the ocean, and this was something I absolutely didn't know when we started this, supplying oxygen and also sequestering carbon at huge rates. So now both are heating up, our atmosphere and the ocean. And one thing we know about heating things up is it causes those things to behave differently. So our last chapter, chapter 8. Is measuring change. So while Heather writes, Heather and I are sitting here in the television station in Olympia, Washington, and where we're sitting right now was once covered in glacial ice 5 times the height of the Seattle Space Needle. Climates change.
Without the planet yet.
Yeah. So what we're looking at the size of we're looking at the Space Needle. So 5 times the height of the Space Needle. In fact, right outside my back door, there's a large rock, and when the glaciers came down, they carried a lot of rocks from Canada. They're called erratics, which means traveler in Latin. And outside my back door is a large erratic rock that came down from Canada in the Pleistocene when the Ice Age was here. It's pretty amazing. We also have trees that were knocked over down in our creek bed that were growing on the top of the glacier. And when the glacier melted, they fell over and got buried. It's really interesting. So climates change. Because there's a direct relationship between CO2 levels and temperatures, we can use the measurements of CO2 levels to tell us about the past climates. So Heather just posted a graph, and this graph is called the Keeling curve, and she's drawing an arrow there to an island in Hawaii, Maui, and that's where he took his first measurements. So in 1957, a young geochemist named Charles Keeling began recording the levels of CO2 in the air. His measurements are now known as the Keeling curve, and there he is. So there's where he started. And it's famous because for the first time, it's scientifically measured and established that CO2 levels are rising. And there they go. So you can compare the level in 1957 at 313 parts per million. I was 6 years old then. So this is basically the story of the life of my lifetime. So, and today they are at 420 parts per million. And you can actually go online and just Google it, and every day you can find out what the parts per million are. And you'll notice there's a lot of zigs and zags in it. That's seasonal differences, and but basically you can see the trend. So this amount of, so you might want to ask, is this amount of change common, unusual for our atmosphere? Is this a big deal that it's going up? So to answer that question, we're putting up a second graph. Now, this one is not measured from the air. What they've done is they've gone to glacial ice cores and they've drilled down into them and found pockets of ice from the past. And so they have measured, using this ancient air bubbles that were trapped in the ice, the CO2 levels in our atmosphere back 800,000 years. So that's what you're looking at in this graph. And you can see over the 800,000 years, yep, you can see them going up and down. And then you get to today. And we highlighted that.
Pat's life.
Yeah, yes.
From here to here.
Yes. The change is dramatic. And Heather put that in there. In fact, that's sort of like when I'm born and where I am right now, 71. And we highlighted it because it tended to look like it was the side of the graph, but that's not the side of the graph. There's Heather.
And it's vertical.
Yeah, it's vertical when you put it down there. So is this different than what's happened in the last 800,000 years? It's very different. And we call this one the Holocene because it was a period of stability. And this is the period in which human beings developed. So we can go back even farther in time, and you can drill into the ground underneath the ocean and come up with marine sediment cores, and that gives scientists a general view of the broad climate changes going back 100 million years. So today's CO2 level, we now know, is higher than it's been since the origin of our first ancestors. So here they come.
Oh, yeah.
So the last 3 million years, it has not been. So if we go back 3 million years ago, here are the guys. Homo erectus and Homo neanderthal. So basically, they're coming out of the trees and starting to walk across the African forests. What's causing this unusual and rapid increase in the CO2 in our air? You'll notice that this graph shows the amount of CO2 in the air has been amazingly stable for the last 12,000 years. This period of stability is then followed by a dramatic rise, leading to our current level of 420 today. For the first time, human activity has become the prime changer of our atmosphere. We are releasing large amounts of carbon dioxide by burning fossil fuels with our agricultural practices and with our destruction of the forests. So you got three main things: fossil fuels, the way we plow and grow food, plow the fields and grow food, and our destruction of the forests. Climate is complex, so scientists cannot tell us exactly what will happen from this change and exactly when. But not knowing everything is very different from not knowing anything. And we were talking about how important this is when you have climate denial. There's so much that we do know. Scientists can tell us that there is a causal relationship between periods of higher CO2 levels and the heating of our planet. And they can predict many of the effects of these rising temperatures. And scientists are warning us not only are the levels of CO2 rising, but they are rising at an accelerating rate. And that's what when people refer to a hockey puck graph, that's what you're seeing when all of a sudden it starts rising at a faster and faster rate. They're telling us that we need to reduce emissions now. The Keeling curve is iconic among climate scientists. They thought everyone would pay attention to the changes we were reporting. Scientists thought that the Keeling curve would become as recognizable as this famous portrait. And if you read the literature that was written back then, you'll have scientists talking about how everyone will know the Keeling curve. We all know the Mona Lisa. Try asking someone, anyone, if they know what the Keeling curve is. So we aren't paying attention to what the scientists are telling us. After all this time, I think it still surprises the scientists who keep trying to tell us. Bless their hearts, but it's not working. If we continue to choose not to act, CO2 levels and temperatures will continue to rise at dangerous and accelerating rates. We are commingled with everything else on Earth, Alok Sharma says. Our climate, our world will succeed or fail as one. So, what can you do? I read a lot in the process of writing this, and what you got was a synopsis of probably 35, 40 books that I read. And hopefully we put it together in a brief way where you could see the main topics. You can go back and read more about any of these. But during the process of reading, I found two books that I thought were very informative and inspiring for people. The first one we're going to talk about is The Future We Choose, and it's written by Christiana Figueres. Christiana was the amazing diplomat who oversaw the Paris Climate Agreement. The first part of her book succinctly and clearly explains the different outcomes scientists predict should we, and she basically draws this as two possible futures, okay? Number one, and Heather and I thought a lot about what would we call this? What do we call the future? And we think that you should refer to it as what we will experience. So the future is not some time off in the distance, it is what we will experience next. So future number one, and we make that the path going up because that's the path where our carbon goes up, okay? We continue, and what's so interesting about this is that doing nothing, if you choose to do nothing, to change nothing about what you do, then you are making a choice about the future, and you are choosing number one. So it's not like you have to do something to choose number one. Doing nothing is choosing number one. Now, that's pretty much the path we're on now. We are doing some things. Hopefully we will do more things, but basically you can see that we're on that path now.
I'm going to make this path bigger so we have more chance to get on it.
I think make more space for that. That's a very good idea. I like that. So Heather's creating a really broad path now for number two. Okay. So path number two is if we act now to reduce our carbon dioxide in the air. And it's very interesting because in Christiana Figueres' book, she'll talk about the subtle differences, like if we reduce this much, what do they predict, and if we do that much. So her book is very, very interesting if you really want to know what does this mean. And she does it very succinctly and very clearly. It's just like bite the bullet. I reread them both last night. It's very clarifies for you what is happening. She also discusses how we as individuals can decide what actions we choose. Because we're all different people, we'll choose different actions. Heather is an artist and a graphic facilitator, and I'm a curriculum writer. So we decided to collaborate on climate education projects. So this is the first time we have attempted to do something, a video of us. Yeah. So this has been very different for us. This is a learning curve on a chart for us. We collaborate on education projects for the climate. While I was in the back room writing this presentation, my husband, who's a farmer, was out planting trees and managed to plant 1,000 trees this spring. It was pretty amazing. And yesterday he was just out looking at some of his trees that he planted last year and talking about how wonderful he felt because he was looking up at these huge trees and knowing he planted them. It's really fun to see them. So, and we've enjoyed this process of doing the curriculum. These things do not have to be, they're not, many of them are fascinating and things that you might want to do even if they didn't have a good effect on climate.
And you feel better if you do something.
Yes.
It alleviates pressure.
Yes, yes. And the guilt that we feel about things. So, so the other thing, so we're each contributing in our own ways to a better future. So the other book we had was Drawdown. And the one there's Christiana. Sorry.
I put her up there. They got to see her.
Oh, perfect. Oh, that's okay, good. Paul Hawkins' book, Drawdown. And I enjoyed this book because it puts you with all the people who are solving the problems. And that's a great crowd to run with, you know. So every page is some great person and of all walks of life who's come up with some marvelous idea about what you can do about sequestering carbon, getting it out of the atmosphere. And they're truly amazing. So for example, one of the things that struck me is that he has 100 of them, and in the back of his book, he rates them according to efficiency. And way up there, I can't quite remember, but I think it was like number 7 was educating a woman and sending her to school in a third world country. Well, we should be doing that anyway. I mean, some of these will surprise you of what you can do as an individual. I mean, you don't have to have a farm, or you don't have to be an educator, things that you can do to help. So I, reading the book, fell in love with solar panels, and I have 3 now. So 2 of my solar panels provide all the energy for my home, and my 3rd solar panel powers my electric car. So now my new all-electric car runs on sunlight. So it's very fun. I came over here on sunlight, and I came behind a cement truck who was spewing diesel out of the top. so it's a very interesting. It's a very interesting thing to. The other thing that you can do is spread the word. One way is to begin a conversation or a collaboration. Might be inviting a friend over to watch and talk about these videos and talk about what you want to do. We hope this will be the beginning of many conversations you will have, because people may not listen to scientists, but people do listen to their friends. So we'll end with a quote from Christiana Figueres, which she says, "Even at this late hour, we still have a choice about our future, and therefore every action we take from this moment forward counts."
Thank you, Pat.
Thank you, Heather.
Yeah. And that brings us to a relatively frenzied close. But I think we're an example, too, of you can have fun. Join with friends, make this something that you can do something about. People feel powerless and impotent, and doing something makes you feel better. Join with a friend.
And don't be afraid to take risks, because, Heather and I have not done anything like this. So we really didn't know even how to time this as we came in, and so we took a risk, and it's been fun, and you learn something, and I think that's part of it. So just jump in, and meet all the other nice people that are working on this problem.
Yeah, and remember, you can go back and you can look at all 8 episodes. I'm going to color them in more, and I have a website that I'll put them on.
Perfect.
The Circle Passages, as well as another one. And please share this information with a friend. Be like these guys. Start a walking group or a talking group or you know, look at the different things, including these books. What can we do?
And we will, along with the pictures, we're also going to put the texts.
Right.
So we know we kind of went fast through some of this, and some of it you can look at the picture and go, yep, I remember all of that, got that one. But this is the part where I get bogged down. Or if you want to go back to the 12.5 sextillion molecules.
You can do that I couldn't even write, that I was like, I'm not even going there. Yeah.
So we'll have the text for all of those. And
Yeah.
then we can also put the books in the.
Yeah, and there's a free course on uplifting eco-activism, so you can walk as far down this path as you want to. But
that's
as
wonderful.
always, you know, thank you, Pat, and thank you for being here with us. Welcome to Circle Passages Takes on the Earth, and you'll agree, I'm sure, that an understanding of air is essential. Who knew? Yeah, so thank you.